This is the last lesson of equations of motion at advanced higher level. We're going to be looking at graphs of motion, and this is the final part of this first section. Today, it's lesson 4. We're going to be covering all these learning outcomes here at the bottom of the page. There seems to be quite a lot, but really what we're looking at is we're looking at motion time graphs at advanced higher level. So we're looking at how some of the calculus methods that we've talked about before, differentiation, integration, can be used to interpret information from motion time graphs. The first thing we're going to look at is displacement time graphs. A displacement time graph shows the position of an object at any time. Now this stuff we're going to look at on this particular slide is higher revision work. If you're not sure about this, there's various other resources that you can go to try and catch this up, including some graph videos that are going to be coming up on this YouTube channel. Okay, well the gradient of a displacement time graph shows the rate that the displacement is changing each second. And that's basically the velocity. That shouldn't hopefully come as much of a surprise. At advanced higher level, there's a little bit of new stuff. We're really just taking stuff that we've learned in previous lessons and adding it to what we already know about displacement time graphs. The bit that we're going to add in here is really notation. It's in terms of notation and in terms of a different way of thinking about gradient. So gradient here can be calculated from 2 points. We can get the 2 points and we can do y2 minus y1 over x2 minus x1, and that would give us the gradient. However, if we also know the function for displacement with respect to time, then we can differentiate that function and we can get ds by dt, and that will also give us the gradient. That's particularly useful if we've got a curve. The gradient of a displacement time graph gives you the instantaneous rate of change, or the instantaneous velocity at a point. The wording here really is slightly different, but it's saying exactly the same thing as we've known up to now. If we want to find the instantaneous rate of change, or the gradient at a particular point to get the velocity, then there's 2 ways we can do this. One of the ways is we can draw a tangent to the graph at that point. A tangent is a straight line that only touches the graph at one point. By getting the gradient of the tangent, and the tangent is basically a straight line, so we can just use 2 points on the line, we can get the velocity, or we can get the gradient at one particular point in time, and that would give us the velocity. But it can also be found by differentiation, and that's what we're going to look at next. The advantage of this is that it works for curves too. Velocity time graphs are very similar. In fact, these slides are exactly the same, with the exception of v being substituted for s, as the previous slide. So I'll just run through it very quickly. The gradient of a velocity time graph tells you the acceleration. So dv by dt. It gives you the instantaneous acceleration at any point. Again, if we want to work this out, we have to basically pick a point in the curve. We have to draw a tangent at that point in the curve, and I'm afraid this tangent is not very good. It cuts through the curve at least 2 points here. And that will give us the gradient and therefore the instantaneous acceleration at that point. It can also be found by differentiation if you know what the function is. We can get a lot of information from the area under velocity time and acceleration time graphs too. At National 5, we knew that the area under velocity time graph gave us a displacement. We quite often did it for speed time graphs, and that gave us a distance, but we did it for velocity time graphs too. At advanced higher, there's no difference. Physics hasn't changed. The area under velocity time graph is still displacement. The only wee extra bit that we put in, we kind of mentioned it higher, but very, very briefly, was that the area under an acceleration time graph gives you the velocity. But how do you actually calculate the area under a curve? It's easy enough to do when it's a straight line. You just, or a series of straight lines. You can just divide the area up into rectangles and triangles. But when you've got a curve, it's a little bit more difficult. You can get a rough estimation by counting the boxes, but it's not very accurate, and so it's not suitable for our purposes. However, if you know the function of a curve, you can integrate between limits, and that will give you the area under the graph. Just a wee quick word about what I mean by integrating between limits. The limits, we're going to do an example of this in the next slide, but the limits for these graphs, for the velocity time graph, would be between 0 and 2 seconds. So if we got the area under the graph, or if we integrated the function between 0 and 2 seconds, between definite limits, then we will get the displacement of the object after 2 seconds. And similarly, we could do this if we got the area up to 3 seconds, or 4 seconds, and so on. For the acceleration time graph, we can do the same thing. So in this case, the area shaded would be equivalent to the integral of the function of acceleration against time between 0 and 3 seconds. And that will give you the velocity after 3 seconds. The first problem that we're going to tackle today is to calculate the displacement after 4 seconds when the velocity is given by the function v equals 2t. The graph at the side here corresponds to that function. Our first solution is a calculus solution. We're going to start off by saying that if the function is v equals 2t, and if we know that v is also ds by dt, then substituting that in for v, we get ds by dt equals 2t. We're going to integrate both sides with respect to t, and we're going to integrate them between the limits, for t anyway, between the limits of t equals 0 and t equals 4. And the reason we're doing that is because we want to find the displacement after 4 seconds, between 0 and 4 seconds effectively. Right, when we integrate this, what we're effectively doing is we're taking this function and we're adding an integral sign in front of each side, and we're putting a dt afterwards, means with respect to t. The next line is, in the next line we've basically simplified the left-hand side only. We've left the right-hand side as it is. ds by dt, with respect to t, the way I always think of it is dt divided by dt, it kind of cancels out. It doesn't quite work like that mathematically, it's not strictly correct, but I think it's a useful way of remembering it. And we end up with ds here. Now you might notice we've also put in the limits. We've got the limits of 0 to s, because at the beginning the displacement is 0, and at the end the displacement is going to be s, our unknown displacement. And then similarly for time, our time starts at 0 and we're going up to 4 seconds. Integrating this out, integral of ds ends up being s. I'm afraid it just does. I'm not going to go into that at the moment, but if you just learn that basically. And on the right hand side, the t here goes up 1 power to squared, and then the 2 goes divides into the 2 here. So we effectively divide by 2, and we get 2 divided by 2, and t becomes t squared. 2 divided by 2 is 1, so therefore we're left with t squared here. We know how to evaluate them between the limits. S goes into here, and 0 goes into here. So s substitutes in, and we get s, and 0 substitutes in, we get 0. So it's s take away 0. Doing the same thing here, the 4 substitutes in and becomes 4 squared, and then the 0 substitutes in to become 0 squared. So it's 4 squared minus 0 squared. And that ends up at 16 meters. Now the second solution is far easier. It's far more straightforward. It's the National 5 solution, which is the s equals area under graph. And that's absolutely valid. And it works very well. So you might think, well, why don't we do that all the time? Well, in this case, we can do it quite easily, because the area under the graph is basically the area under a straight line here. We've actually got the triangular shape, which is dead easy to calculate. We can calculate the area of this just by half base times height. It's not a problem. But the problem is that for a lot of the stuff that we're doing at advanced higher, we can't do that because the area is a curve. Is under a curve. So let's look at our second example. We're going to look at a different example. Now I have changed a couple of things here. I've changed the fact that we're not doing velocity against time, we're doing acceleration against time. So the difference here is going to be that when we get the area under the curve, we're going to get the velocity. And we're going to get the area under the curve up to 4 seconds. So we're going to get the velocity at 4 seconds if the acceleration was these values from the beginning. The acceleration is given by the function a equals 2 squared plus 3. So our first solution, doing it pretty much the same way, is we're going to do some integration. We know that a equals dv by dt, so we substitute this in for a here, we end up with this equation. Now we integrate both sides with respect to t, and again we're doing it between limits, and our limits in this case are t equals 0 and t equals 4. We want to find out the velocity after 4 seconds. Very similar to the previous slide, I'm not going to go through it in great detail, but we add the integral signs and we add the dt. And again here, we end up with dv on the left hand side, and a slightly more complex function is going to come out on the right hand side, but not at the moment. We've only looked at the left hand side at the moment. So, as in the last case, dv and the integral sign, that basically kind of cancels out. Again, not mathematically correct, don't ever write it down, but that ends up with velocity. And again, we start off at a velocity of 0, and we're ending up at a velocity of v. That's what we're trying to find out. The right hand side here is a little bit more complex, but it's still integration. So the t squared becomes t cubed, and then we divide it by 3. So 2/3 t cubed, and then on this side, plus 3, well, this is like plus 3 times t to the power 0. Remember, t to the power 0 is 1. So this is basically 3 times t to the power 0, and then that goes up to t to the power 1, which becomes t, and then we divide by 1, which makes no difference. So that ends up becoming 3t here. And again, the limits are 4 and 0. If we evaluate that, it's a little bit more difficult. The left-hand side is v minus 0, that's straightforward enough. The right-hand side, though, what we have to do is we have to get the function here where t is 4. So we've put 4 into the function here, and that's that bit there. And then we take away the function when v is 0, t is 0. So when t is 0, this whole function, this whole expression ends up being 0. So we're just taking away 0 here, and that makes it a little bit easier. We simplify that out, we end up with a velocity of 54.7 meters per second. Now in this case, solution 2, the area under the graph, is pretty much impossible. Again, we could do an estimation, and we could actually come up and say that, well, 1, 2, maybe we could say, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, perhaps 11 boxes. We could do that method, and each box would be 1 times 5, so 5 for each box. 5 times 11 is 55. It actually works reasonably well, but it doesn't always in that situation. So the reality is that a lot of the time we do have to use integration here.